Okay, so now we are going to see how we can calculate the minimum fluidization velocity. And this is important because whether we are going to operate with a fluidized bed or a fixed bed, we need to know this value. If we want to operate with a fixed bed, then we need to make sure that the velocity is less than the minimum fluidization velocity. And if we want to operate with a fluidized bed, we need to know what is the minimum velocity that's needed to operate the column. So this is this is important. So based on experiments, it was found that the fluidization of a packed bed starts when the force obtained from the pressure drop, the force due to the pressure drop, which is delta P times A, across the bed is equal to the net weight of the bed, which is the gravitational force minus the buoyant force. So this is something that we got experimentally, that if we know how to find the force due to the pressure drop and the force of the gravity minus the buoyant force, then both will be equal. So this is the basic equation that we use to calculate the minimum fluidization velocity. So this is delta P multiplied by A. This is the pressure drop. And keep in mind that the minimum fluidization velocity deals with the bed when it first starts to fluidize, which means that it's static bed till this point. Any more increase in the velocity will lead to being a fluidized bed. So this is the pressure drop of the static bed. Of course, this is the area of the bed, and this is what we have here is the particle density minus the fluid density. So this is the gravity minus the buoyant force. So this is W minus FB. And we multiply them by 1 minus epsilon because it only affects the solid particles, or the volume of the solids, meaning that 1 minus epsilon node times AH node. H node is the height of the bed. So AH node is the total volume of the bed, but the gravity and the buoyant force doesn't affect the whole volume. It affects only the volume of the solid. So this is why we multiply it by 1 minus epsilon node. And now we can divide both sides by area, and we, as I said, this is the porosity at the minimum fluidization velocity. Rho P and Rho F are the density of the particle in the fluid. A and H node are the area and the length of the bed at the onset of fluidization. And this is why this is important. H node is the height at the onset of fluidization. So the height will change with the fluidization, as we said, as we saw in the video before the previous. So this is why we just do the calculations at the onset of fluidization before the bed fluidizes. So the pressure drop is can be calculated from this equation. This is the pressure drop due to the friction of the fluid with the particles, which is equation. And this is the pressure drop due to the gravity, okay, which is rho fluid G H node, or you can think of it as the term of delta Z in Bernoulli equation, which is the head, because the flow is going from down to up, so there is force downward, which is rho G H node. Okay, so this is the left hand side of the equation. And usually this term is not like a significant term compared to the rest, but we'll see. Anyway, so when we combine the two equations, this is the delta P, and this is the right hand side, which is the buoyant force or the gravitational force minus the buoyant force. So we can rearrange the equation, so we can put all the u square or put the constants together. We have the u square here, we have u node here, and we have the rest of the constants here. And as I told you, the term of the rho fluid GH node is not like a significant term. Usually the particle density is in the range of thousands, and the fluid density and fluidization is mainly for gases. So for the fluid density is in the range of ones or something around this. So this term is going to be negligible, and this term is going to be negligible as well, so you can put it as rho P. It's going to be a very, very valid assumption, or approximation. Anyway, so this is the equation that we use to calculate the minimum fluidization velocity. And as you see, it's a second order polynomial equation that in U node. So this is why we will get two roots, and since this is negative and this is positive, we will get two roots. One is negative and one is positive, and the positive value of the velocity is what we consider. So let's just check this case. We have air with density 1.21 kilogram per meter cube and the viscosity of 18.3 times 10 power minus 6 kilogram per meter second. It flows upwards through a sand bed. The sand particles are uniform. So we know the average diameter is 0.2 millimeter. So we have the particle diameter here. We know the density and the viscosity. And 0.3, this is before fluidization, so this is the minimum fluidization velocity, and the raw particle is 4,500 kilogram per meter cube, and the height of the bed is 10 meters. We want to calculate the minimum fluidization velocity. So what we'll do is just to check the equation and see if we have everything. So we have here the particle density, we know the fluid density, we know the particle diameter, we know epsilon node, we know the viscosity of the fluid, we know everything. So it's going to be just substitution in the equation, and we'll get a second order equation where we'll have two roots, one positive and one negative, and from this we can take this as the minimum fluidization velocity. So this is what we do with this. I don't think there is other thing we need to know about the packed beds, concerning what we are covering here. So we'll stop here, and we have one more chapter left in this course. So we will see you in the next chapter, inshallah. Goodbye.